All right, welcome. So my name is Filip, and this is a session about what I think is one of the most fascinating topics in all of technology, and that is, of course, quantum computing. So first of all, thank you all for coming. I really appreciate you coming. I really do. Because this is sort of a niche topic in many aspects, especially as, quantum computing is not really that particularly useful for anything at this stage yet. So from that perspective, I was not expecting that people would show up. I was actually worried that nobody would show up. And, we are not going to learn anything particularly useful because of that as well. However, I hope that this session, this next hour, will sort of give you a little bit of a glimpse into the future in terms of how our computational models might look like going forward. And I hope that this session will also encourage you to dive deeper into this fascinating field. Quantum computing sits at the intersection, I'm going to move the mouse, sits at the intersection of physics, computer science, mathematics, a little bit of chemistry, maybe even philosophy, as we will learn in this session. So there is something there for everybody. And so if you'd like to dive deeper after this session, and I also have a book recommendation for you. So this is a sort of a companion book to this session. It's a book that I wrote last year, and it takes you all the way from the basics of quantum mechanics to writing quantum algorithms. And this is the company that I work for, and I am actually based in Switzerland. So let's begin by having a look at the bigger picture, okay? Now it might seem like quantum computing is actually some sort of a latest craze or latest fashion trend out of Silicon Valley, but that couldn't be further from the truth. In fact, quantum computing as a scientific field dates back to the early 80s when Richard Feynman famously suggested that in order for us to be able to simulate nature, to simulate the processes going on in nature, the dynamics of natural processes, we should be building computational models that are quantum mechanical at their core, rather than be binary. And this is effectively the definition of a quantum computer. It is a device that is performing its calculations or its computations using the principles of quantum information theory. And throughout this session, we shall sort of unpack what this really means. For now, we could say that the consequence of this is that quantum computers can actually harness the power of the quantum effects. And those are really weird and really strange and really bizarre if we consider them from our everyday macroscopic perspective. So first of all, there is the superposition. So a quantum object can actually be in many different states at the same time. And this, of course, doesn't seem to make much sense. But that is a consequence of the mathematical formalism of quantum mechanics. Then we have entanglement. Quantum objects can actually become entangled with each other. And once they do, they can exhibit correlations that are impossible for us to reproduce in our everyday macroscopic world. Then we have wave-particle duality. So quantum objects can actually behave like a wave, so be sort of spread out spatially, or they can behave like point-like objects, depending on how we choose to interact with them. And finally, there is randomness, this uncertainty that is built into the very fabric of our reality. And all of those things we shall explore in one way or the other throughout this session. But before we get there, a very brief historical outlook or historical view. In 1985, David Deutsch, who despite his last name is not German but actually British, a brilliant physicist from the University of Oxford, he developed the first universal model for quantum computation. And to this day, this is really, from the mathematical perspective, this is how we think about quantum computing. Then in 1994, Peter Shor of IBM developed what is still today one of the most amazing algorithms that we have for quantum computers. This is the integer factorization algorithm. Now, it doesn't seem like anything particularly exciting, but it achieves exponential speed up over the best known classical alternative, which means that for certain types of problems, quantum computer, a sufficiently large quantum computer, would be able to solve them probably in a matter of minutes, maybe hours, and a classical computer would require millions, if not billions, of computational years. And we also know that given a sufficiently large quantum computer and sufficiently stable, the algorithm that Peter Shor developed can be used to break most of our currently used public-private cryptography schemes, such as RSA or elliptic curves. And of course, this is quite a big deal because that is effectively what underpins the security on the internet today. Then in 1998, the first quantum computer was built. It was a tiny machine consisting of 2 quantum bits. It was using a technology called nuclear magnetic resonance. And interestingly enough, this is the same core technology that is used in MRI scanners. So the next time you are at the hospital and you see an MRI scanner, you can sort of think of it as a cousin of a quantum computer. Then in 2016, IBM launched the first cloud platform for quantum computers. And this was a big deal because it sort of democratized quantum computers, right? Like you no longer have to be a postdoc or a researcher at a really good university with a really good quantum program, but you can actually access quantum computers, as we would say, from the comfort of your own keyboard. And now other providers like Amazon with their Bracket service or Microsoft with AzureQuantum offer the same type of access to quantum hardware through their cloud platforms. Now the way you can think of quantum computers, and I mean this is a very crude picture, so we should not spend too much time on it, but just to provide a little bit of structure, you can sort of think of quantum computers as sort of co-processors to your regular program, to your regular CPU, that simply sit in the cloud, right? And so on this picture, the blue line here, this is what we would say classical computing. So when we speak about regular conventional computations, from the quantum perspective, we would often call them classical. So in the most crude form, we can break down the program into input, then the workflow execution and the output. And as your program executes, at some point it might decide, you know what, this particular task or this particular routine is actually suited for a quantum computer, which means you would call an orchestrator that sits in the cloud that is able to take your input and convert it into the state that can be fed into a quantum computer. And that state then evolves according to the laws of quantum mechanics, and we shall see what this means. And ultimately, we need to extract classical bits, so as zeros and ones, out of the quantum computer. And this happens through the process called measurement. And those bits can then flow back to your original program. Again, the information density in the slide is probably quite low, but at least it provides a little bit of a structure. So we shall dive deeper, of course, as we progress with the session. But before we get there, I wanted to also offer a few words of warning, because there's a lot of quantum hype in the media. So first of all, we currently find ourselves in an era that is called noisy intermediate scale quantum computing, which is a very fancy way of saying that quantum computers make a lot of errors at the moment, and they are not really useful for much. Right? The second thing is that even though we speak about quantum computers, we really only have quantum processing units. There is no quantum storage, and there is no quantum memory. At least, I mean, there's a lot of research in that space, but there's nothing that is integrated together with the processing unit. So effectively, we just have quantum processing units. They are very limited in terms of their input and very limited in terms of their output. They can do interesting things when the program executes, but that's about it. So that is worth mentioning. And finally, even if we have in the future much bigger and much more stable quantum computers, which is what we expect we will have at least, we think that they will never really become general purpose computational devices. They would be extremely useful for some specialized use cases, and in those cases they might actually revolutionize the specific field. But I think regular silicon-based computation will not go away. So what are the use cases where we think quantum computers will be useful? I mean, it goes back to the original suggestion from Feynman. Pretty much anything that is at its core a quantum mechanical problem, especially chemistry, right? Molecular simulations, drug discoveries, material science. All those things can actually be mapped quite easily to the dynamics that go on in quantum computer. So those are the types of problems that we think we'll be able to solve. I mean, in general, you could imagine a situation where just about any chemical reaction could be simulated on a quantum computer without actually using any chemicals, and that would be tremendous. Then climate and energy research, again, this is stuff that at its core is quantum mechanical, so we think we will be able to map those problems quite well. Now going outside of the realm of quantum computing and more into the space of quantum communications, we know that quantum communications can provide us with security that is actually underpinned by the laws of nature, so effectively unbreakable security. So there is a lot of research in terms of building, for example, quantum internet. Then machine learning is an active area of research. So people are trying to combine machine learning or more broadly AI with quantum computations. However, the major hurdle is of course the the input and the output limitations for quantum computers, because they are really not that suited for the so-called big data problem. And finally, optimization. So all kinds of optimization problems where, you know, the different paths to the solution have to be explored, you know, especially in logistics, maybe also in financial simulations. We think that quantum computers will be very good at that. Now, for the purpose of this session, we are going to be using Q# for the examples and also AzureQuantum. So I wanted to spend a few moments talking about this just to make sure that everybody's on the same page. Now, all the theory that we shall cover is actually independent of Q# and AzureQuantum, and it's equally applicable to other tech stacks. So Microsoft has this quantum development kit, which allows you to build quantum programs either using Q#, which is a dedicated quantum programming language, or Python, which is usually the language that's preferred by the academia. If you have a .NET development background, you would feel somewhat at home with Q#, I think, because the toolchain is quite similar. I mean, the development happens in VS Code. You would be building your program using .NET CLI. You would be using packages from NuGet. So actually, Q# packages are hosted on NuGet and so on. It is, of course, not a .NET language because there is no .NET for quantum hardware, but the toolchain is somewhat similar. Then Quantum Development Kit is actually a family of libraries, so it's not just the core quantum library, but also libraries that can help you get started in different types of fields to which quantum computing might be applied. And finally, you can build sort of standalone applications. You can think of them as a quasi quantum console applications, or you can actually use Jupyter notebooks for more interactive experience. And you can, up to a certain size of a program, you can simulate it locally. And of course, you can also submit it to AzureQuantum. And AzureQuantum is a quantum platform that supports Q# programs. It also supports programs that are built with Qiskit or Cirq. And those are two of the most popular quantum computing frameworks for Python. Then in AzureQuantum, of course, you get access to real quantum hardware. Now, interestingly enough, there is no first-party hardware from Microsoft. So Microsoft is building their own quantum computer. This has been announced. But they have actually chosen a technological path that is much different from all the other vendors. And because of that, they are actually on a completely different timeline. And there will probably not be a quantum computer from Microsoft for quite a few years still. There are 3 providers currently that supply hardware to AzureQuantum. One is called IonQ, the other is called Quantinuum, and the third one is called Rigetti. So these are all startups in that space. Now, we also have access to simulators in the cloud. So those are vendor-specific simulators, so they can be a bit more accurate than the simulators that are locally in the Quantum Development Kit. And finally, you get free credits per provider. You get actually $500 per provider to spend and try out stuff. And the typical interaction path with AzureQuantum would be to use AZCLI, which is the command line tool to manage your Azure subscription. And for that, there is an official quantum extension that can be installed. And effectively, you can submit your program as a so-called job for execution. And once your program is submitted, it gets typically placed in a queue, because as you can imagine, the quantum hardware resources are really scarce. So you have to wait in a queue. Unless you pay a lot of money to Azure, then you can bypass the queue. And ultimately, you can fetch the output of your program once it executes. And the output might look like this, and if it doesn't make much sense, then should not worry, because we are going to have a look at this in a moment. And from the more architectural standpoint, the way this works is that there is an Azure Quantum workspace that you have to create for yourself in your Azure subscription. And behind it, there is a storage. So you also have a storage account. And effectively, your program gets uploaded to the storage. And from there, it gets queued for execution on a specific provider, which could be a simulator, or it could be a real quantum hardware. And ultimately, once your program completes, then the result is written back to the storage, and it can be fetched from there. And all this orchestration is done by the quantum extension of AZCLI. So we are going to look at the code in a moment. But before we get there, a little bit of theory. So classical information theory is actually relatively simple. I mean, we can fit it on one slide. Everything is a 0 or a 1, and this is the end of the theory, right? Now, quantum information theory is a bit more interesting. So in quantum information theory, the basic unit of information is a quantum bit, a qubit. And mathematically speaking, it is described not by a 0 or a 1, like a bit, but instead it is mathematically described by a vector, a two-dimensional vector, consisting of two numbers, alpha and beta, complex numbers, by the way. And those two numbers have to fulfill just one condition, which is actually shown here. I can actually see. And this is the so-called normalization condition. So this is really the only requirement. And that already implies that a qubit can be in one of infinitely many possible states, because we can find infinitely many alphas and betas to satisfy this equation. Now, it gets even more interesting once we start adding more qubits. So once we add a second qubit, well, it has its own alpha and beta, so it is also described by a two-dimensional vector. And now quantum mechanics tells us that in order to provide the full description of this composite system now consisting of two qubits, we have to calculate the tensor product between the two vectors. And in linear algebra, a tensor product between two two-dimensional vectors produces a single four-dimensional vector. Now, if we add a third qubit, then the vector would become eight-dimensional. And we can sort of generalize this by saying that a quantum state vector for a program consisting of n qubits has a mathematical description that consists of 2 to the power n dimensions. Or in other words, every time we add another qubit, the dimensionality of this vector will double. And this is precisely why performing quantum simulations on a classical devices, on classical computers, is pretty much impossible, because we very quickly run out of memory. And here is a good example for this. So this is a molecule of penicillin, right? It's not a super sophisticated drug. And basically, in order to describe the quantum state vector of, or in order to write down a quantum state vector of a molecule of penicillin, we actually need 10 to the power 86 bits. So this is in order for us to be able to capture all the spin orbitals of all the atoms involved and so on. And this is a huge number, right? It is so big that we estimate that this is more than the amount of atoms in the entire universe, which we think is about 10 to the power 80. So in other words, if I wanted to simulate fully the molecule of penicillin on my laptop, or in fact, for that matter, on the fastest supercomputer in the world, I would have to use the entire universe as my memory. Now, in principle, the same thing can be done on a quantum computer with 286 logical qubits. Logical qubits means error-free qubits. And the reason for that is simple. 2 to the power 286 is roughly 10 to the power 86. So a quantum computer has access to this sort of vector space that allows it to perform this type of simulation. So we know at this stage that a qubit is much different than a bit, but they have one thing in common. So a bit can only be a 0 or a 1. Now, a qubit can be in one of infinitely many states. We already said that. But quantum mechanics puts quite a severe restriction on us. Namely, it only allows us to distinguish two of those states from each other at once. So effectively, only two of those states are observable to us. And the states that are typically used are the mathematically simplest cases where alpha is 1 and beta is 0 and vice versa. And these vectors are actually shown here. And this symbol here that we have, so this symbol here and on the other side, this is a so-called ket. So ket 0 and ket 1. This is a notation from quantum mechanics. And it's just a shorthand way of writing a vector so that we do not have to write the full column, but instead we can write the shorthand symbol. Now, this also allows us to map a state of a qubit to a classical bit. So if we see a qubit in a state ket 0, we will treat it as a bit 0. And if we see a qubit in state ket 1, well, then we will treat it as bit 1. And this, of course, works in the opposite direction as well. If I want to input a 0 into a quantum computer, then I will create a state ket 0 in a quantum computer. And if I want to input a 1, I would create a state ket 1. The state of a qubit can be visualized on what is called the Bloch sphere. So at least the mathematics of the qubit can be visualized on what is called the Bloch sphere. And this is a sphere, and we start at the center. And if we draw a vector to quote-unquote north pole, this would be our vector ket 0. And the vector that starts at the center and is drawn to the south pole, this is the vector ket 1. And again, these are the only two states that we can actually observe in a qubit. But actually, any other vector that we draw from the center of the sphere to the surface of the sphere is also a valid qubit state. So what about all these other states then? Well, it could be a state like this. So there is a red arrow here. And that state is not a state ket 0 and is not a state ket 1. but it is actually a linear combination, mathematically speaking, of both ket0 and ket1. And this leads us to the most important equation that we will see today. This is a general equation for a state of a qubit, alpha ket0 plus beta ket1. Notice that when alpha is 1 and beta is 0, we simply have a state ket0. And when beta is 1 and alpha is 0, we have a state ket1. But if they are both non-zero, then we have a vector that doesn't point to the North Pole, doesn't point to the South Pole. It might be like this red arrow that we have on the slide. And this is a superposition state, because in that case, both alpha and beta are actually non-zero. And this state is there, but it is actually something that we cannot observe, right? So we can rely on the fact that it's there. We can try to use it in some calculations, but we will never be able to see it. So we can never ask a qubit what state you are currently in, and it will say, well, thanks for asking, I'm in a superposition, right? What happens when you try to observe or measure a qubit that is in a superposition state, it will actually collapse to either ket0 or ket1, and this is the so-called quantum state collapse. And the outcome of that is probabilistic. And this is why we say that there is uncertainty that is built into the very fabric of our reality. I'm going to repeat this because it's really important. It is actually a fundamental quantum doctrine. And this applies not to just quantum computers, it really applies to everything in our world, right? That an observation or a measurement of a given quantum property does not reveal a pre-existing value of that property. It is in fact quite the opposite. The outcome of the measurement or an observation of a quantum object is brought into being by the sheer act of observation itself. And this has very deep philosophical consequences, of course. You know, the brilliant Austrian physicist Anton Zeilinger said, the world is not as real as we think, because effectively the default state of the world is a superposition state, and only through observations or through measurements, the quantum objects are forced to collapse to observable states. Now, this is something that we will not dive into in this session, but what we can say is that even though this is probabilistic, we can calculate those probabilities, and this is the best that we can do. And the rules here are super simple, actually. The alphas and betas are actually probability amplitudes in this case. So the probability of collapsing to ket0 is simply absolute value of alpha squared, and probability of collapsing to ket1 is absolute beta squared. And again, remember, when alpha is 1 and beta is 0, we said we have a state ket0, but what we really have is we have a 100% probability of a collapse to ket0, and vice versa. When beta is 1 and alpha is 0, we have a 100% probability of a collapse to ket1. But if they are both non-zero, so when we are in a superposition state, there is some probability of collapsing to ket0 and some probability of collapsing to ket1. And this is also why we had this normalization condition to begin with. Because those numbers squared, when we add them up, they have to add up to 1 because they represent classical probabilities. And together, this whole thing is called the Born rule. And this was developed by Max Born in the second half of the 1920s. And Max Born actually went on to win the Nobel Prize for that. And to this day, this is one of the postulates of quantum mechanics. But the remarkable thing is that this is not derived from anything. And I don't want to trivialize this, but it was effectively guessed. And it has just always been correct, right? So now at this stage, what we can do is we can sort of summarize what is the main difference between a classical program and a quantum program. So a classical program has some input, then it executes whatever workflow it wants to execute, and it has some output. And at each state, it operates on bits. So the bits come in, then the bits get shuffled around, and then ultimately the bits come out. And at any point in this process, we can actually pause the execution of a program. We can look inside the CPU register, like we can unpack everything. Everything is fully transparent. In fact, everything is deterministic as well. Now, in a quantum program, it's a bit different, because we can also only input classical bits into a quantum computer. We have to encode them as states ket0 or ket1. Then the program executes. And when the program executes, the qubits can enter the superposition state. They can become entangled, which we'll talk about in a moment. They can explore this state space that they have access to. So in this case, these are 3 qubits, right? So they would have 8 dimensions, like 8-dimensional vector to sort of explore. But it could be a lot more, of course. But this is actually not accessible to us. It's a black box. Like, we can think what is happening inside there. We can try to nudge it into a certain direction. But it is something that we cannot observe. Because as soon as we try to observe the result of the computation, the quantum states, like it's shown here, they would collapse to ket 0 or ket 1 for every single qubit, which effectively means, since this is a mapping to classical bits, that classical bits come out. So the major difference is during the program execution, actually. And the outcome, of course, like we said, is probabilistic, right? So the task of a quantum algorithm is to try to tilt those probabilities towards the correct answers. Now, Einstein hated all of this, right? And this is the title of this session. So he famously said, God does not play dice. You know what Niels Bohr responded when Einstein said that? He said, Einstein, don't tell God what to do. So, and the thing with quantum computers is that we will not be telling God what to do, but we can actually play God because we can actually try to organize the qubits into a real program that does something. And the way we do this is by building up circuits. And this is sort of conceptually similar to logical circuits that we can build on a CPU or with bit logic at the lowest possible level of interaction with bits, right? So this is, I think, something that most people have seen at some point in the computer science education. And effectively, we can take bits and we can apply logic gates to them, and this way we can build up any algorithm. Now, it is somewhat similar in the quantum world, where we have qubits, and we can build up qubits into circuits. And from there, we can actually have effectively a program that executes. And the gates, the logical gates, in this case, in quantum computing, are actually linear operators from linear algebra. And the reason why they are linear operators is, of course, because the state of a qubit is a vector. So how do we act on vectors? Well, we can act on vectors by multiplying them using matrices. And effectively, all those gates here, so on this diagram here, each horizontal line represents a qubit, and then the symbols here are gates. So each of those gates is a matrix. So here there is a matrix that is applied to the middle qubit. Then this weird symbol is actually a 2-qubit gate. So it acts on qubit number 2 and 3, and so on. And effectively, as those matrices are applied to the vector states of a qubit, the vector state would change. And this is how our program evolves. So what does it mean? Well, here's an example of such a gate. So it's an H gate, one that is used quite often. It is named like this after French mathematician Jacques Hadamard. And it has a matrix representation that looks like that. And the reason why it is useful is it can take a state ket 0 or ket 1, so effectively one of the initial states, because this is how we can encode information in the first place into a quantum computer, and create what is called a uniform superposition. So we can go through this calculation and see why this works. So if we apply H to the vector ket 0, then of course the matrix representation of H is something that we know already. And then the state ket 0 actually has a vector representation 1 over 0. And if we calculate this, this is what we end up with. This is the vector. So alpha is 1 over square root of 2, and beta is 1 over square root of 2. And if we recall the equation that we saw earlier, alpha ket 0 plus beta ket 1, so we can rewrite it this way. And this is the ending state, like after this operation. So what does it mean? Because alpha and beta are both non-zero, this means we are now in a superposition. And since we can use the Born rule to calculate the probabilities here, we can apply the Born rule, we can square alpha and beta, and what do we end up with? 1 over 2. And that means that there is actually a 50% probability of collapsing to ket 0 and 50% probability of collapsing to ket 1. So effectively, our qubit is now in a state where it is effectively a perfect quantum coin toss. In fact, it is now a coin toss that is underpinned by the laws of nature, which is something that you can never achieve on a classical hardware. Now we are going to continue with this in a moment, but I wanted to take a short one-slide detour into the behavior of waves. So waves, and this actually applies to all the waves. So waves on the surface of water, sound waves. I mean, light behaves like a wave as well. When two waves meet, they interfere with each other. And they can interfere either constructively or they can interfere destructively. And in the first case, this is the first example or extreme case where two waves are identical and they are what we would say in phase, so they are aligned perfectly. And so when those two waves meet, they would create a bigger wave. And in the second case, the waves are actually shifted by half a wavelength. And so when they meet, they would actually cancel each other out. And why do I bring this up? So if we go back to our qubit state, so we applied H to it, and now we are in a state that looks like this. if we now observe or measure this qubit, it would produce randomly ket 0 or ket 1, and we would have our random bit. But what if we don't observe it yet? What if we apply h again? What's going to happen? Well, we can do the calculation, right? So we take h, we take our current state, and the matrix of h is something that we know. And this state, alpha is 1 over square root of 2, beta is 1 over square root of 2, so this is a vector. We do this calculation, and we end up with 1 over 0, which is effectively a state ket 0. So what happened is that the qubit was forced out of the superposition, and now it's just in a state ket 0. So what happened here? Actually, interference happened. So the probability amplitude here and the probability amplitude here is effectively described by a wave. And so the two waves that represent the probability of collapsing to ket 0, they get amplified and they become 1. So they go from 1 over square root of 2 to 1. Whereas this probability wave, because of the destructive interference, gets reduced or cancelled out to 0. And this is how we end up with the state ket 0 at the end. And the reason why I bring this up is that this is one of those key things that you need to do in quantum algorithms. You basically want to amplify the correct results and sort of cancel out the incorrect results. And overall, the strength of quantum computers is actually this ability to compute stuff in the superposition and be able to take advantage of that, including also constructive and destructive interference. And this is what we, in general, would call quantum parallelism. And the definition of quantum parallelism, or the way you can think of quantum parallelism, is given a function f of x, instead of evaluating f for different values of x, you can pass a superposition of all the possible values of x and try to calculate from there. Now, this is very subtle, actually. The whole effect is very subtle, so we should not read too much into this, but this is actually the way to begin thinking about this. And this actually leads us to the most basic logical problem that a quantum computer can solve in a more efficient fashion than a classical computer. This is the so-called Deutsches problem. And so you're given a function that takes in a bit input and produces a bit output. And the task is to determine if the function is constant or balanced. Now, because there is just one bit input and one bit output, there are only 4 possible cases or permutations, right? So let's unpack them. So it's either whatever you input, there is always a 0 that comes out, which is the first case. This is a constant 0. And we have a constant 1. So whatever you input, 0 comes out. So basically, the other way we can say that is the function returns the same thing for all the inputs, right? And in the other 2 cases, the function returns different things for different inputs. So we input 0, 0 comes out, we input 1, 1 comes out, and we input 0, 1 comes out, and we input 1, 0 comes out. And these 2 functions at the end, they are balanced. So now, classically, using classical logic, you have to evaluate the function twice to be able to determine if the function is constant or balanced. Here is a decision tree for that, but just using common sense, imagine you input 0 into the function and 0 comes out. Well, you have no idea if this function is constant 0, or is it actually balanced, right? So you have to input 1 to determine whether the function is constant or balanced. Now, remarkably, a quantum computer can do this in a single evaluation of the function by using a superposition. And so this is the quantum circuit that can achieve that. And now, in order to unpack this circuit, we would have to actually dive into quite a bit of linear algebra, which is actually something that I wanted to avoid in this session. So instead, what I will suggest that we do is we have a look at an analogy. So this is the analogy that I came up with. And this is a siblings analogy, right? Just like as it is the case with all analogies, we should not push it too far, but it should hopefully illustrate what a quantum computer can do that the classical computer can't. So imagine we have 2 sets of siblings. One set are identical twins on the left, and then we have regular siblings on the right. We can only ask them one question: how are you doing? And they can only answer good or bad, right? So the identical twins will always answer the same thing, right? Good, good, or bad, bad. And the regular siblings, because they would always fight, they always say the opposite thing. Now, we have basically now reconstructed Deutsches problem using siblings, and it should make it a bit, I think, more intuitive to understand what is going on. So now imagine that you are in a dark room, which actually conveniently we are in a dark room. But so this is my dark room now. And imagine that there are 2 people in there, 2 siblings. You cannot see them, but you can ask them questions. You can ask, how are you doing? Now, classically speaking, you have to ask them one by one, because that is what regular computer can do. It can only invoke the function, by passing in a 0 or a 1. So a classical computer would ask the first sibling, how are you doing? And the answer might come back, and it's good, right? Now it would have to ask the second sibling. The answer comes back good, and now we know these are identical twins, right? It might have played out differently as well, right? So we ask the first one, we hear bad, but we still have to ask the second one. Now we hear good. This means that these are regular siblings. Now here's what, and this gets a bit shaky because it's just an analogy, but here is what a quantum computer would do. Now, a quantum computer can ask in a superposition. So the quantum computer asks a question, and both siblings get the question. So they both answer. However, because of the quantum state collapse, right, we cannot observe a superposition. When we try to observe a qubit, there would be a quantum state collapse. So we can only hear one answer. So we cannot hear both of those answers. That would be too easy. But here's the thing. Imagine that these are identical twins, right? So they answer the exact same thing. Now the two sound waves representing their answer interfere constructively. And what we get is we get a louder answer. And from that, we can actually infer that these are identical twins. And similarly, if these were regular siblings, they would both get the question, they would both answer, but they now answer different things. So their answers now interfere destructively, and we hear just gibberish in this case. And so from that, we can infer that these are identical, these are regular siblings. And this is effectively the gist of it, right? So this is the analogy. So now going back to our quantum circuit, this is effectively what we would reach if we went through the linear algebra. So we would find out that using our qubit, if the qubit collapses at the end to ket 0, it means that the result of an execution of a function for f of 0 and f of 1 is actually identical, right? So basically, in that case, the probability of collapsing to ket 0 gets amplified. Whereas if f of 0 and f of 1 return a different result, which means the function is balanced, not constant, then the probability for collapsing to ket 1 gets amplified because of the interference, the constructive interference. And this is effectively the gist of it. Again, this is quite a subtle thing, and it helps to go through the mathematics, but I hope that the analogy helps. So at this stage, what we can now do is we can have a look at some code, finally. So is this large enough, or should I make it larger? I don't see anybody anyway, so I'm not sure if you're nodding. Yeah, so here's the most basic Q-sharp program that you can have, right? It is a program that allocates a single qubit. It then places this qubit in a superposition by applying the H transformation, and then it performs a measurement, so it observes this qubit. And at this point, the qubit will collapse with 50% probability to ket 0 or ket 1, which is effectively something that we can then map to a classical 0 or a classical 1. So I'm going to run this, and I'm going to run this, I'm going to run this using an orchestrator that will execute this program at 10,000 times so that we see a probability distribution. This runs on the local simulator that comes with the quantum development kit. And notice what happens. We get a probability distribution that we were sort of expecting, right? So 50% zeros and 50% ones. Now we said that if I apply H twice in a row, what we should get is, because of interference, we should only get zeros again. And so if this now executes, we should see now that we get 10,000 zeros, right? So of course we can build up this example further by creating a random number generator, right? So in this case, what we are doing, we are allocating 16 qubits. This is an array syntax of Q-sharp. So we now have 16 qubits in an array. We will place each of those qubits into a superposition by applying H to every single qubit. This is a helper operation in Q-sharp. I could have done it in a loop, for example. That would have worked as well, of course. And then we have to extract classical bits out of those qubits. So we do this by measuring the qubits. And in this case, the multi-M operation measures the whole array. In fact, what it does really, it goes through every single qubit in that array and measures them individually. But again, it's just a convenience in Q-sharp to be able to operate on an array without having to loop through it. And we get results out of this, right? And those results are either zeros or ones. They are random, and so we can convert those random bits into an integer, of course. And so I'm going to run this, and this should give us a random unsigned 16-bit integer. And again, the randomness here is underpinned by the laws of nature, right? It is not simulated randomness like it is the case of classical computers. So if I run this again, I should get a different number unless I'm super lucky. So there you go. So what we can now do is just to see the probability distribution. I'm going to change this. And I'm going to change this to just 2 qubits. And I'm going to execute it again. Now, because I changed it now to 2 qubits, this is a 2-bit integer now. So it's a number between 0 and 3, right? 0, 1, 2, and 3. But the reason why I wanted to do this is just so that we can see the probability distribution and notice that this is exactly what we were expecting, right? So 25% cases, we get 0, 1, 2, and 3. OK, so the next thing that we can do is we can actually submit this to AzureQuantum to have a look at how it would feel in AzureQuantum. Unfortunately, because AzureQuantum is a preview service, it is mostly down since yesterday evening. So we will not be able to do this. I mean, we can try. So what I'm going to do is I'm going to submit it to the provider called Azure Q. So I'm going to show you what this does. So here is a program that I'm trying to submit. It's effectively the same program that we just saw, except it uses 4 qubits, so it's a 4-bit random number. And the script that I just executed, it's going to submit it to AzureQuantum to the IonQ ARIA1 quantum processing unit, which is their newest quantum processing unit, and also to the IonQ simulator. So this is now being submitted, and we can see that it was actually placed in the queue, and we get an ID back. So what I can now do is I can jump over to AzureQuantum, and let's see what happens in AzureQuantum. Now, this is something that you can set up for yourself if you wanted to. It is in public preview, so anybody has access to this. And once you have provisioned an AzureQuantum workspace, you should jump over here to the providers. And then you can add a provider, right? I have already added all of them. And these two and the last one, IonQ, Continuum, and Rigetti, these are the vendors that provide quantum hardware. And normally Rigetti is the one that has been the most stable one, but unfortunately since yesterday it is actually unavailable. Now, then we have IonQ. And so IonQ, you can see these are the different targets. So this is the old quantum processing unit that they have. It's not available anymore. It was actually taken out. The ARIA one is the newer one that they have, but unfortunately the wait time in the queue is a week. So let's meet here next Friday. The simulator is available though. And then Quantinuum, it has more targets, but the relevant ones are unfortunately degraded. So long story short, we can jump over here to the job management, and you can see the jobs that I have submitted. And so these are the 2 ones that I have submitted. And the quantum processor job is unfortunately stuck in waiting, and then the simulator one has completed. Now, I tried the different ones yesterday, and they are all stuck in waiting state. And this is unfortunate because for all the previous days, I was actually checking this every day because I was worried that it would not work. And it was working every single day. So anyway, what we can do, however, is we can at least fetch the output of the simulator in this case. And for that, I have a command, a helper command. And so this is the helper command. And let's see what the simulator tells us. So in this case, the simulator would tell us, I mean, it should not be particularly surprising. Oops, I think I made a mistake here. Let's try it one more time. This. And this one. So the simulator tells us that, I mean, this program, because it's generating a 4-bit random integer, it has 16 possible outcomes, and they are all equally likely. So, you know, from that perspective, it's not a particularly exciting demo, but in a way, it is quite cool, even though it is not working at the moment, that you know, it is possible to interact with real quantum hardware from your own laptop. I mean, in many aspects, quantum computers are some of the most sophisticated machines that the human mind has ever built. So, you know, just being able to interact with them in the cloud is quite cool. Now, the last thing that I wanted to show you here is the Deutsches algorithm. And in this case, we have the 4 functions, constant 0, constant 1, balanced, same, balanced, opposite. They are implemented here. But as it was the case with the Deutsches algorithm, they are sort of considered a black box, so we should not even look at them. And basically, this is the implementation that was there on the quantum circuit that we had on the slide. And this algorithm, what it does, it will run Deutsches algorithm for all 4 functions, right? And the first 2 functions are the constant functions, then the 2 functions are balanced functions. And remember what we said? When the algorithm produces a 0, it means it has detected a constant function, and if it produces a 1, it has detected a balanced function. So what we can now do, we can run this, and again, I'm going to run this using the orchestrator. The orchestrator will run 10,000 times, and it should produce 10,000 times the result 0011, which is exactly what we were expecting. So if you'd like to dive deeper into this, I'll have a link to this, to all these demos at the end. So let's go back to the slide. The final thing that I wanted to talk about is entanglement. And in many ways, entanglement it is actually even weirder than superposition. So how can we create entanglement? Well, we can do this using the C0 gate, a controlled NOT gate. And it has a matrix representation that is shown here. Now you might ask at this point a question, why is this matrix bigger than the H matrix? Which is actually a very good question. Thank you for asking. So it's a really good question. So the size of the matrix of representing the logic gate in this case corresponds to the amount of qubits that it acts upon. So the H gate acts on the single qubit only. Because the single qubit state is 2-dimensional, the matrix has to be 2 by 2 as well. Now the C0 acts on 2 qubits. A state of 2 qubits, because of the tensor product, is 4-dimensional, and therefore the matrix has to be 4-dimensional as well. And what this gate does, it treats the first qubit as a control and the second qubit as a target. And it will flip or apply the NOT logic to the target if the control is in a state ket1. So in other words, we can draft a sort of a truth table. So this is our first qubit, the second qubit, right? Control target. And in the first 2 cases, because the control is in a state ket0, well, effectively nothing happens. When we apply C0, there is really no change to our qubits. But in the second of the bottom 2 cases, because the control is in a state ket1, the target gets flipped. So it gets flipped from ket0 to ket1 and from ket1 to ket0. Now you might actually object at this stage and say, well, there's nothing quantum about this, right? Because we can plug in here regular bits or booleans, and it would work the exact same way, and that is true. However, we can also ask an interesting question, namely, what happens when the control is in a superposition? Now, we already said that when the qubit is in a superposition, we can consider it to be in both states ket0 and ket1 at the same time. But if in the C0 gate it is supposed to flip the target, if it is in a state ket1, then when it is in a superposition of both ket0 and ket1, would it flip or would it not flip the target? And the answer is both. It would both flip it and not flip it. And effectively, we can calculate this, right? So we can take 2 qubits in state ket0, apply H to the first one. This creates a superposition over the control. And now we apply C0 to both of them. And once we go through the calculation, this is what we end up with. And this looks very much like a superposition state that we saw before, except it now spans across 2 qubits in a way. I mean, superposition is sort of contagious. It has spilled from one qubit into the other qubit now. And what this tells us is that when these qubits are observed, they would both collapse to ket0 or both would collapse to ket1 because they are entangled, right? So for the time being, both of them are both ket0 and ket1 simultaneously. But when they get observed, they would both collapse to ket0 and both collapse to ket1 with 50% probability. There is never going to be an outcome where one collapses to ket1 and one collapses to ket0. This is entanglement. Now it doesn't seem like much, but it completely destroys our understanding of reality. Because here's the thing, quantum mechanics also tells us that an entangled state cannot be decomposed into a tensor product of the individual quantum states. Now this is a fancy way of saying that from the perspective of quantum mechanics, the smallest possible unit of reality now is this entangled pair of qubits or particles or whatever you entangle. They do not exist as independent entities anymore. There is no mathematical description in quantum mechanics to actually separate them anymore. They have to be considered as one. But the problem is, we can send one of them over there and we can send the other over there. in principle, they could be at the opposite ends of the universe, and still quantum mechanics would tell us that they form one thing, and we have to consider them together. Now, this is quite interesting because both of them are actually in a superposition. So when we measure them, one of them, it would collapse randomly to ket 0 and ket 1. When the second one is measured, they would sort of synchronize themselves to make sure that they produce the exact same value. Now, Chinese researchers, they have a quantum satellite in the low orbit, and they can actually create entanglement in the satellite. And they can beam one of the particles in the entangled pair to a ground station in China, and the other to a ground station in Europe. Now, what you can do, for example, is you can time the measurement of those particles to the fraction of a second to ensure that no influence can propagate between them. Not even light has enough time to travel between them. And yet they would always produce the exact same value. Now, Einstein hated it, right? He called it spooky action at a distance. And he spent a lot of time trying to prove that this is incorrect. And he had this idea that, you know what, there is no randomness here at all. It is all predetermined. Like he basically said, when they get entangled, they agree on what they would collapse to. Let's agree to collapse to ket 0, then they go their separate ways, and then they collapse to ket 0. Then there is no mysterious influence or synchronization happening. But he actually never found a mathematical solution for this. And the reason is because he was wrong. In 1964, at CERN in Geneva, John Bell came up with a brilliant mathematical proof that showed that the correlations exhibited by quantum objects, entangled quantum objects, are stronger than anything that you can pre-encode into them. And we call this non-locality. And locality means that, effectively in physics, locality means that no influence can propagate faster than the speed of light. And last year's Nobel Prize in Physics was won by Alain Aspect, John Clauser, and Anton Zeilinger, who over the 1970s, 80s, and 90s developed a series of experiments that basically showed that entanglement is really there, and that John Bell was right and Einstein was wrong. Now, we don't really know what entanglement is. Like, we have no way of capturing or even explaining what it is, other than there is this mysterious link between the two particles. But amazingly enough, we can take computational advantage of entanglement in quantum computers. So that's what we can do. So here is a program that actually creates entanglement. And it does exactly the stuff that we talked about moments ago. So it would allocate 2 qubits, a control qubit and a target qubit. It then places the control in a superposition by applying H transformation to it, and then it applies C0 to both of them. And at this stage, line 12, the qubits are actually entangled. So what we can then do is we can measure them. We can measure them in any order that we want, and both would collapse to ket 0 or both would collapse to ket 1, but there would be no other possible outcome. So let's try to run this. Again, this will run in an orchestration of 10,000 executions, and notice in half of the cases we get 2 zeros, and in half of the cases we get 2 ones. Now, we can extend this further by building a random number generator that is now entangled. So in this case, we are going to allocate 8 qubits, and we will call them Alice. Then we will allocate another array of 8 qubits, and we call them Bob. And we shall entangle those 2 qubit arrays. And this is using a helper operation from Q-sharp, prepare entangled state, but really internally it actually does a loop and the H and the C0, all the stuff that we discussed so far. And effectively we now have 2 arrays that are entangled. So elements at index 0 are entangled together, elements at index 1 are entangled together, and so on. So we have 8 pairs of entangled qubits. Now here at line 23, I mean, if you squint your eyes, you can imagine that Alice takes her qubits and goes one way, and Bob takes his qubits and goes the other way. In fact, we could send those qubits maybe using a quantum communication network. I mean, in principle, one of them could fly to a different galaxy, doesn't matter. What matters is that at some point, they can measure their qubits. And at that point, they would really receive a random number, because the qubit will collapse to either random ket zeros or their set of qubits will collapse to a random set of ket zeros and ket ones. So effectively, they get a random set of bits. But they can be sure that their counterpart, wherever the counterpart is, will receive the exact same random numbers upon measurement as well. And so basically this program runs in a loop of 100 executions and keeps track of all the numbers and make sure that they are all the same. And this is really the case, right? So in 100 out of 100 cases, the measurement is the same. Now, what is the consequence of this? So let's say Alice is there and Bob is there, and they have now the same random number. Well, a random number or a random set of bits is nothing more than, for example, an encryption key. So they can use this to engage now in a symmetric encryption. And here's the thing, though. The difficult thing in symmetric encryption is actually the key distribution. Now, in this case, the key was effectively distributed through entanglement, right? So one of them had their own set of qubits, the other had their own set of qubits. They didn't really have any value until they were measured. When they got measured, they acquired the value, which was somehow synchronized to their counterpart. Now imagine that you are an attacker and you would like to attack this and steal the key. Well, there's nothing for you to attack because no information traverses the space and time between Alice and Bob. And when Arthur Eckert came up with this protocol in 1991, in his PhD thesis actually, he called it quantum key distribution without an associated element of reality. And if you think about this, this is just so mind-boggling, and this is not science fiction, right? Like, it just describes technology that we are able to already use today. Okay, I think at this point we have done everything. Thank you so much. If you'd like to see those slides, that they are online, the demos are also online. If you happen to open these slides, you can click here to go to a shop and buy my book. There's actually a promo right now. You can get it for 16 euro. And I think that's it. Now, I used up almost all of the time. So, and also there's a lunch break. So my proposal is that we don't do any questions, but if you'd like to talk about anything that we covered here, just come up afterwards to me, grab me, and I'd be happy to talk about anything. I also have one other thing that I wanted to say. I have one copy of my book that I'd like to give away. So just the first person that comes up and says they want a book, you can have it. Thank you so much again for coming. I really, really appreciate it. Thank you.